Hi, welcome back to the lecture series on algebraic topology. After a long time, we have we have been continuing with our lecture series. So, just have a recall that what we have done so far. We were interested to study in homotopy theory, and we have covered a lot of portions so far, that including what is homotopy between continuous function. Okay, so the homotopy between two continuous functions are following. That suppose f is a mapping from x to y and g is a mapping from x to y, such that f and g both are continuous. Then f is said to be homotopy with g if there exists capital F is a mapping from x cross I to y, such that f of x comma t such that f of x comma 0, this is small fx, and f of x comma 1, this is small gx. Mean that suppose we have let's say here I have x and here I have g. If we have a map, let's say here it is f and another map, let's say here it is g, then basically there are some in between maps that can extend this small f to small g. Means you can traverse from small f to small g via all these intermediate threads. So that means what is the structure of these intermediate maps? The maps should come like this, that each ft should be defined from x cross x to y, such that ft of small x equal to f of x comma t. Okay, so these are these ft's. So it is ft's. These are all the ft's. Okay, these are all the ft's. Okay. Alright, so now again one can define another map. Let's say if x is a mapping from I to y, such that fx of t equal to f of x comma t. So that means for this is for every small x belongs to capital X. So that means this fx can be defined as a path from fx of 0 to fx of 1 in y. Okay, so from once you have these once you have two maps and want to define the homotopy between them, then this capital F not only gives you these intermediate threads, but also gives you some path in these topological spaces that can join the points of intermediate steps, right? So let's have an example. For example, a most common example you have seen, that is something called straight line homotopy. So the straight line homotopy, suppose we have f comma g, both are mapping from x to R2. So note that as R2 is convex set, okay, R2 is convex set, hence if we take any 2 points, then you can join them by straight line, and that particular straight line will be complete inside R2. Alright, so if you have these two maps, and let's say it is any two maps, Alright, then you can define the homotopy between f and g like way that suppose we have, let's say, is my R2, okay, so it is my R2 plane, and let's say one curve is like this and another one is like this. Just a second please. Another one is like this. Okay, then what are the straight line homotopies? Like, say if you have take any particular small x, let us take f of x1 and g of x1 where x1 is fixed. So let's say here is my f of x, so it is, let's say it is my g and this is my f. So on f of x1 I have this one, and let's say g of x1 I have this one. So these 2 points can be joined by a straight line, right? Thus for every small x belongs to capital X, I can join fx and gx like way. Okay. Now note that I haven't mentioned where's the direction actually, but direction should be like this, should be dependent on the map that you have chosen. For example, suppose let's say consider here the definition of homotopy between the continuous functions. Fx of 0 is nothing but small fx and fx of 1 nothing but small gx. That means basically I want to, by this condition actually this implies that I should traverse from f to g only. Okay, and similarly, so if I want to define from, let's say, small f to small g, that means let's say I want to get this kind of maps. So the homotopy maps should be from fx to gx that I need to get. So then just like this. Okay, means you can pull it down and overlap with this, and then push it down to get overlap with this. Ultimately these two will be overlapped with this. Okay, so again if you want to get a reverse direction, then you have to pull it back, pull this line over, and it should overlap with this one, and if you have to push it down and to overlap with this one. Just mean you have to just deform the structures actually, right? Just bend these straight lines and make this or make the curve straight. So whatever be the condition, that doesn't matter the direction. So based on the direction the map should be changed. For example, if we want to get some fx to gx, so that means the maps should be from fx to gx. So the straight line, initial point of the straight line should be fx and final point of straight line should be gx. So that means the homotopy, that is fx of t, this should be nothing but t times gx plus 1 minus t times fx. Okay, so you see that what is fx? 0. Fx is nothing but small f of x, and fx of 1 nothing but g of x. Remember, this is the condition or the equation of straight line that we should define in case of between two particular points in a convex set, is nothing but this particular equation gives us paves the way. Alright, so that means this is the fxt. So my map f is a mapping from x cross I to y such that, let's say y is nothing but R2 here, such that f of x comma t is nothing but fx of t. So basically either you get two maps between fx to gx like way, or maybe the converse one. Okay, means either this particular map you should get these fx, this kind of paths from each point, paths from between each points on the required continuous functions, or you should get such ft's. Okay, whatever be this. So either you get these threads, or you get the correspondence between f and g, particular points on the f and g. All right, so this is how one can define the straight line homotopy. And likewise, suppose we have two paths actually, because path is also a special kind of continuous functions. By the way, we have the homotopy between two continuous function is not unique at all. Okay, that is homotopy between two continuous functions is not unique. So I have proved it in last in the lecture videos. So just you try, or otherwise if you can't get it properly, otherwise then just move to the lecture 1 of LTOP, whatever you find. Alright, so then in case of path also you can define the homotopy between two paths. For example, suppose we have gamma 1 and gamma 2, these two are paths from I to x. Then gamma 1 and gamma 2 are said to be homotopy if and only if there exists capital F from I cross I to x such that f of s comma 0 is gamma 1s and f of s comma 1 it is gamma 2s, and f of 0 comma t it is gamma 1 0 same as gamma 2 0, and f of 1 comma t is nothing but gamma 2 1 same as gamma 1 1. Okay, by the way, we can define the homotopy between the two paths if and only if gamma 1 0 is same as gamma 2 0, and okay, not if and only if number 1 gamma 1 is gamma 2 0 and gamma 1 1 equal to gamma 2 1. Means if we have two paths in topological space, let's say one path and this is my another path, so the initial point and the final point should be same, otherwise we cannot define the homotopy between two paths. So at that time, what are the intermediate threads? The intermediate threads are like this. So intermediate threads are like ft is mapping from I cross I to x such that ft of small s equal to f of s comma t, and that means you know that these are the ft's. So from here you can observe that for every ft of 0 it is f of 0 comma t is gamma 1 0 is same as gamma 2 0, and ft of 1 is nothing but f of 1 comma t it is gamma 1 1 same as gamma 2 1. So that means for a path homotopy, the initial and the final points of each of the intermediate threads should be same. Okay, so the first coordinate, the last coordinate, that is map, should be like f of s comma t. Okay, so the last coordinate basically gives the roll number of each of the threads, and the first coordinate gives a speed, how fast it is moving from this curve to this curve. Okay, in fact you can change the speed like way that how we can join into homotopy max. For example, suppose we have to another homotopy, another map like this. So like is another homotopy map. So whenever this one is homotopic to this one, so this one is homotopic to this one, then that means this one is also homotopic to this one. So let's say the intermediate homotopy maps between let us name this as, let's say it is gamma 1, it is gamma 2, and it is gamma 3. So here these are the intermediate maps, let's say. Intermediate threads. So once you want to traverse from gamma 1 to gamma 3, means first half time to traverse from gamma 1 to gamma 2 and next half time gamma 2 to gamma 3. That means it actually gives you this motivation that you can join these two maps. For example, suppose we have f1 is from I cross I to x, such that f1 of s comma t is one map, and f2 is mapping from I cross I to x, as that okay, f1 of s comma 0 is gamma 1 s, and f1 of s comma t, this is gamma 2s, such that f1 of s comma 1, this is gamma 1 s, and f1 of s comma yeah, that is right. And f2 of gamma s, so this is 0, this is 1. f2 of gamma s1, it is gamma 3s. So the map between required map to show between gamma 1 and gamma 3 is nothing but f is from I cross I to x, such that f of s comma t is nothing but, so the first half, that so we have to say that in the first half time you should traverse from gamma 1 to gamma 2. So just make t belongs to 0 to half and t belongs to half to 1. So it should be nothing but f of t minus 1. So what is 0? At 0 it is 0, and at 1 is f of s, f1. Yeah, this is f1, this is f2. Okay, this is how one can define join any two homotopy maps. So this is how one can easily prove that the homotopy between two maps is nothing but equivalent condition, is both equivalent to each other. All right. In fact, the same motivation can be obtained from in case of joining any two path. Let's say you have a path gamma 1 and another path gamma 2, then we can join these two paths as like that. Gamma of t is nothing but gamma 1 of 2t, gamma 2 of t minus 1, t belongs to 0 half 1. Okay, that means it is nothing but in the first half time we should traverse by gamma 1, gamma 2. Okay, all right. And in case of loop, as loop is also a special kind of path, you can define the path homotopy between two loops. For example, suppose that is just gamma 1 0, gamma 1 1, gamma 2 0, gamma 2 1. This is a particular point x naught, and rest of all the properties should be set. Just the picture representation will be get some different. That is, suppose we have here we have one loop, then homotopy should be like this. This is like we can define homotopy maps. Okay. Alright, so this now the collection of all homotopy maps, homotopy loops based at x naught are said to be as fundamental group based at x naught, that is pi of x naught. So it is nothing but equivalence class of gamma such that gamma is from 0, 1 to x, such that okay. Alright, now we have promised that we will prove the group axioms of fundamental group, and we'll see some more applications of fundamental group. So now let us begin with our main discussion today. Now, that is group axiom fundamental groups. So remember that suppose let's say gamma and delta, this belongs to pi 1 of x comma x naught. Then how I define the group operation, that is gamma times delta is nothing but the concatenation of gamma star delta. Okay, now first axiom that we like to prove is an associativity. And let us consider that if G and H both are mapping from I to X, such that f of 0, G of 0, H of 0, this is same as f of 1, this is same as G of 1, same as H of 1, thing but x naught. Okay, so that means each are basically loops. So let's say here it is f, here it is G, and for example let's say here it is H. Okay, so it is my G F H. So what's my claim? F dot G dot H is nothing but F dot G dot H. So what is my F dot G dot G? Nothing. It is nothing but F star of G dot H. Okay, so that means it should be here that F star G star H. Okay, so what about F star G star H? So F star of G star H that we have just defined is nothing but let us say, first it will go by F star G of 2s H of 2s minus 1. So where for all s belongs to 0 to half, here s belongs to half to 1. Now if we again break this condition then it will be like this. So 0 to half will be defined as 0 to 1 by 4, 1 by 4 to half. So it is f of 2s, it is g of 2s minus 1. Alright, no, sorry, I think, no, wait a minute. Okay, no, not 2s, it is 2 times 2s, right? So it is 4s. It is 4s, it is 4s minus 1. Okay, so that means I basically broken 0 to half, 0 to 1 in 3 segments, right? One is 0 to 1 by 4, next is 1 by 4 to 1 half, then half to 1. On the other hand, what about f star of g star h? It is nothing but f of 2s. It is g star h of 2s minus 1, where s belongs to 0 to half. Here s belongs to half to 1, right? Now again break half to 1 into different segments. It is g of 2 into 2s minus 1, and it is g of 2 into 2s minus 1 minus 1. So here it should be s belongs to, so half to 1, just break it in second part. So it is half to 3 by 4, and s belongs to 3 by 4 to 1. Okay, means just half to, just like 0 1 1 by 4 half 3 by 4, so half to 3 by 4, 3 by 4 to 1, right? So this is how one can, oh sorry, this should be h, so you can write it as g of 4s minus 2 h of 4s minus 3. Okay, so how we can define homotopy between these two maps? The homotopy between these two maps will be defined the following way, that, so by the way, just let us have a picture representation. So it is my 1, and let's say and let's say it is 0 to 1, it is 0 1 0 0 1 0 0 1 1 1. Okay, so let's say at certain point it is my t, right? I have broken it in two parts. One, it is t to 1 by 4 is half, 0 to 1 by 4 and half to 1. So first it is f, it is g, it is h, and later f is defined from 0 to half. So here it is my half in 3 by 4. So note that initially it is f, when in this case f star g star h, f is acting from 0 to 1 by 4, So that means f is acting 0 to 1 by 4. And next one, f is acting from next case f is acting from 0 to half. So that means I can join these two particular path. So these two paths can be joined. Similarly, note that in case of G in case of upper portion, G was acting from 1 by 4 to 1 by 2. Latter half to 1 or 3 by 4 means is acting like this. So here it is acting like f to G, and it is like, so it is come like this. So I can join these two as well. And you see that for H it is anyway getting managed, like H was mapping from half to 1, here H was mapping from 3 by 4 to 1. So you see that it is anyway getting managed like this. Okay, so now H will be mapping. So now it is very easy to define from this aspect. So H is mapping from I cross I to X such that H of S comma T. So it will act over F and G as well. So this, try to get the coordinate of these 2 points is nothing but S equals 2 minus T by 4, and it is S equals 3 minus T by 4. Okay, so it will be just like F is a mapping from F of 4S into 2 minus T, where T belongs to where S belongs to 0 to 2 minus T by 4, and for G it will be acting G will be acting from 2 minus T by 4 to 3 minus T by 4. So it will be just like G of 4S plus T minus 2, where S belongs to 2 minus T by 4 and 3 minus T by 4, and H is nothing but 4S plus T minus 3 by 1 plus T, where S belongs to 3 minus T by 4 to it is 1. This is 1, right? So just we have, you should get confused how these equations should come. You just try to get the equation of these two lines, then you'll easily can get it. Okay, all right. So this is how one can define the H between F star G star H and F star of G star H. That means via these homotopy maps, F star of G star H, this one and this one, both are homotopic with each other. So that means F star G star H is homotopic to F star G star H. So this homotopy map is actually works. All right. So F dot G dot H is nothing but F dot G dot H. Okay, so associativity is satisfied. All right, now next is the identity one. So what should be the identity one? You can easily the most natural guess for identity one is that take the identity map. So that means just define that, let's say E x naught is mapping from I to x such that Ex naught of small x is nothing but x naught for all s belongs to capital I. So that means it is just a particular, every time just a particular point, small x naught. This is constant map. So now again, what is F star ex naught, f star of ex naught is nothing but f star of ex naught is nothing but f of 2s, where s belongs to 0 to half, and ex naught of 2s minus 1, where s belongs to half to 1, there is nothing but 1. F of 2, I mean, here it won't be any change, but here it should be x naught. Okay, so what should be the map? That again, just try to get the picture like this. So here it is my 0 1, it is 1 1, it is 0 0, it is 1 0. So initially when f star of ex naught, f is acting like this, half, and rest of the thing is x naught. But in this latter case, I mean, I need to show that this is homotopic to f as well. So now in case of f, it acting from entirely I. So that means just these two lines can be joined. So just join 0 and half. Okay. So, and okay, anyway, just take t here, and it is making a point up to this t by 2. This is t by 2, this is 1 minus t by 2. Okay, so here we find h is a mapping from h of s comma t as, h is a mapping from I cross I to let's say x. Okay, so that h of s comma t is nothing but f of s by 1 minus t by 2, and it is x naught, where s belongs to 0 to 1 minus t by 2, and s belongs to 1 minus t by 2 to 1. In fact, this coordinate is 1 minus t by 2. The left, I mean, the y coordinate is, just note this picture that it is it's not like that it has just coordinate is 2 minus t by 4. I mean, just I need to make sure that this distance 1 minus t, 2 minus t by 4, this particular distance is t minus t by 4. This is how one can visualize this concept. I'm not bothered with the another coordinate, just bothered with an s value only. Okay, all right. So this particular map, this works as a homotopy. Homotopy between f of x e star x naught to f. In fact, we can change the. In fact, we can change the order of ex naught. Like instead of this, we can make another one that is. Can this ex naught star f. So here it will be ex naught of x, means it is x naught, and here it will be f of 2s minus 1. So that means then the picture will be something different. That time f should be work. I mean, that time f should work in between this. These two parts should be f like this. F should work in this region. So that means it should be like this. Okay. So this is how one can define the map. So that's why then again changing the order, we can define the homotopy between them and can get that it is homotopic to f. Okay. All right. So this is how one can show that this identity map is there. So ex naught means, so what is the identity one? Identity is nothing but the coset of ex naught, this map. Okay. And another one is the inverse So inverse is something like this, that suppose we have f is a mapping from I to x, then f bar, so note that f is a mapping from I to x means what? It is basically a loop, right? So that means I can either traverse by clockwise or by anti-clockwise. So I can take f bar to be just as a defined orientation. So if f is traversing clockwise, then f bar will be just the same map traversing anti-clockwise, and if f is traversing anti-clockwise, then f bar will be traversing clockwise. So that means f bar just a opposite orientation of f. So f bar is nothing but f of, let's say, 1 minus s. This is the. So what about f bar now again? F star f bar, it is f of 2s, and it is f bar of 2s minus 1. So it is 0 to half, it is half to 1. So what is f bar of 2s minus 1? It is f of 2 minus 2s. Okay, so again the map structure is like this, and 0 to half it is f, and okay, I need to show that the isomorphic to x naught, right? So again x naught is working through all over the I. So first take 0 to half, next again half to 1. So then these are the required intersecting points. So here the homomorphism h of s comma t, this will be work-like. So this is t by 2, and this is 1 minus t by 2, and so that means it is just like h is nothing but f of 2s into 1 minus t, and it is f of 2 minus 2s into 1 minus t. So it here half to 1. Okay, so then f star f bar is same as x naught, and the converse one is also as well possible. Alright, so this is how one can show that inverses exist. Okay, so that means the pi or pi 1 of x comma x naught, this is said to be the first homotopy group, or fundamental group. And it satisfies group axiom. So the question one can easily ask that, is it abelian? Means that suppose we have two loops. Let us consider here is one loop, is another loop. Okay, so once you traverse in this particular loop, if you have this one, then again traverse this one, and reverse direction, if you first traverse this one, then again traverse this one, both are not same. So every time it may not be equivalent to each other. Okay,